Okay, so doing something a little bit different here. I decided. Well, I've always this quarter has been rough, right? So it's because we're doing remote learning, and it just feels like this pandemic has been dragging on for so long. And I've done my best to try to adapt this course for kind of remote learning, and I've put in every effort to try to avoid making this class more difficult than classes in the past. It's I know exams are open note and open book, but it's not my desire to try to compensate for that by making exams extra hard or something like that. Okay, and so when I was looking through grades, I was a little concerned because I saw kind of a greater proportion of students having grades lower than 70%, which is kind of my cutoff for a C, which is what students need to pass to kind of get credit and stuff. And so I decided to do a grade book analysis, right? And so first I wanted to look at the distribution of midterm scores, midterm 1 and midterm 2 scores, and I'll show you what I found. And I mean, so I'm a stats professor, so like data analysis, this is my jam anyway. So so anyway, here's kind of a two histograms plotted right on top of each other. In blue, we have this year's midterm 1 scores. In salmon, we have the past midterm 1 scores, okay? And I would say we have pretty close alignment between this year and previous year's midterm 1 scores, okay? And if I do a comparison of kind of the quartiles and medians, they line up quite closely as well. So, Q1 is, 72 versus 74 this year. Previous year's 84 versus 86, Q3, 93 versus 94. I'd say we have pretty good alignment between previous years and this year's, and again the histogram between this year and previous years align for midterm 1. If anything, we've had more people scoring 100 this year. And then here I've plotted the empirical CDF. Like, I'm so excited that you guys know what an empirical CDF is, right? So because I can show you these plots and you understand what's happening. Whereas like if I showed these to anybody else, they'd be like, what am I looking at, right? So what we're looking at in red is this year's empirical CDF versus previous year's empirical CDF in black. And basically, if you see the black and the red line up, that means the kind of the two distributions are very similar, okay? And so so this is what we see. We see pretty close alignment between the black and the red. And then I also ran the KS test, which you guys are also familiar with. And so the KS test kind of comparing the older midterm 1 scores and this year's current midterm 1 scores, I get a p-value around 34%. So so basically my conclusion is that the data do not provide evidence that this year's distribution of midterm 1 scores is significantly different from previous year's midterm 1 scores, okay? Because previous years I also had kind of the similar structure of midterm 1, midterm 2, and a final exam. All right, so then I looked at midterm 2, okay? So midterm 2, this year's in blue, previous years in kind of this orangish salmon color. Pink, I don't know what color we call this. Okay, and again, I would say we have pretty close alignment. Maybe previous years we had a few more people scoring 100, but overall, pretty good alignment, okay? And if we compare Q1, the median, and Q3, also pretty good alignment. So in previous years, 78 versus this year, 77, previous year's 90 for the median versus 88 this year for the median, and Q3 98 versus 96.5 this year for Q3, okay? And again, this is based off 153 scores for this year and accumulation of around 432 in previous years. Okay, and again, here is the empirical CDF, and again, close alignment between red and black, indicating a good sign of similar distributions of scores. And similarly, the KS test for midterm 2 also produces a large p-value, indicating that that this year's distribution of midterm scores is, well, we don't have evidence that they are significantly different between these distributions here. Okay, so I was wondering, what explains kind of the difference, just at least what I perceived to be a difference in grade distributions, overall grade distributions. So anyway, all to say, based on the data analysis, I believe I've managed to make this year's midterm exams comparable in difficulty to past midterms exams. Okay, despite kind of changes in being remote learning, being open book. I think we're in kind of comparable territory. Okay. I decided to take a look at the homework grades. Okay, and so my homework grades have actually, I've been kind of recycling homeworks from previous years because, because I like the homework assignments that I have, and I think, it's my intention for them to be good learning tools. And so anyway, I decided to do an analysis of homework grades, and so what I'm looking at is any assignments that scored 0 points, so basically missing assignments. Okay, and also assignments that scored less than 50%. And that also includes missing assignments. I just did a check for less than or equal to 50%, not a between 1 and 50, between 1 and 50 points, okay? Just because in general, in the past, most students who kind of complete the assignment, maybe they may make a few mistakes, but would score at least 80 points on the homework or something, even with a few mistakes or something. So this is a comparison of proportions, okay? And so what I, in the past, basically completely missing homework 1, usually less than half of 1%, okay? So maybe in, if I had 200 students that year, maybe I'd be missing 1 assignment total or something. So less than 1/2 of 1% is missing homework 1, whereas this year we're close to 3%, 2.6%. Homework 2, similar things. This is 0.2% versus around 2 percentage points missing homework 2, and for homework 3, just around 1% missing homework 3, and again close to 3%, 2.5, 2.6%. Okay, and then as far as scores that were less than 50 points, okay, homework 1 around 3% this year versus, again, less than, all of these in past years were around less than 1%, with homework 3 maybe around 1%. This year we have around 9% of assignments scoring less than 50 points on homework 3, and similar for homework 2. So here's just kind of the raw counts. This year we're missing a total of 11 missing assignments among 153 students. 153 times 3 is 459 assignments. So out of 459, 11 are missing, whereas in previous years, among 432 students, there are a total of 1,300 assignments. Basically, I was missing a total of 7. Okay, and then this year, as far as homework scores below 50, we have around 26 among 459 versus 11 out of 1,296. So just kind of looking at these numbers straight up, just looking at how many assignments are scoring low values, it seems like a vastly different proportion. But of course, being in the stats department, we have to conduct tests, right? So I ran a proportion test just to verify, is it truly different? So I said, is the proportion of, 11 out of 459 versus 7 out of 1296, is that significantly different? And the answer is yes. Our p-values, less than, 0.2 of a percentage point. Okay. So the difference we're seeing in missing homework assignments can't be explained by random choice alone. And then similarly, when I check for low scoring assignments, assignments with scores less than 50 points, we get a p-value, on the order of 10 to the negative 9, which says the difference in missing assignments can't be explained by random choice alone. And as far as the gradebook goes, the only other part that's included in your grade is right now so far is lecture viewing quizzes. And I have nothing to compare that against. So I'm not able to do a comparison there. But to me, this is, I think this confirms what I was what I've been suspecting has been going on this quarter, because I think this is kind of also what I've been feeling, is that basically what the tests can tell me is that students are just as capable this quarter as they have been in past quarters, that it's not like people have lost their, capacity to do intellectual stuff. But, I find myself having trouble finding motivation to kind of get work done and things like that. And I think basically, the pandemic, distance learning, this kind of feeling of disconnection and social isolation and all of that, I think that's taken its toll. All right, it's been going on for a long time. I think it's taken a toll on kind of our mental health and our motivation and all of that. And and I'm just kind of looking over the grades, and I've had the privilege of having many of my students, many of you for many quarters, and so I know that the students who are missing assignments, these are not lazy students, okay? Students did well in 102A, students did well in 102B. 102B was also distance learning, but I feel like, I don't know, maybe because it was like, we had just started distance learning, maybe it was easier to stay motivated. I don't know, right? I just know that right now, like it's been hard. Going into, whatever the 9th month of this, and I don't know if there's an end in sight. So for, I think a lot of students taking this class, 102C, I think almost all of my students are seniors. I mean, maybe I have a few third years, but most of my students are seniors. This is kind of the last course in the 102 series, and you need this class to kind of get credit to complete the major and graduate. And so, okay, so I'm splitting this up. I don't want to actually post all of these score things onto CCLE, so you can watch the video again, but I don't want to actually post my slides of the scores on CCLE. So anyway, these are the notes that are being posted. So I've decided to make just a few changes to my grading schema. These are minor changes, and I think these are designed to kind of help the students who seem to be struggling the most, and kind of basically, I don't want to fail a bunch of students who are scoring, lower than 70% or things like that. Okay, I want these students to graduate. Okay, and so I don't want to. So I'm changing a little bit of my grading schema. Okay, I've always kind of used a straight scale in the past, and I still believe in the philosophy of a straight scale, that that the grade you get at the end of the course shouldn't be a mystery, where you have to kind of guess where you stand in comparison to other students, right? And so basically, I'm going to publish this adjusted straight scale here, and then you can kind of look at your grades and figure out where you stand and know what you'll expect you know, as far as a final course grade, without having to guess, like, you know, am I in the upper half, I'm in the lower half, things like that, okay? So, so anyway, pretty much changes to the, I didn't make any changes to kind of my ranges of A scores, because I think as far as students in the A range, there's a lot of things that are kind of, the distribution, I think the count of students getting A's has been fairly consistent this quarter versus previous years. The biggest changes are kind of in this lower range here, okay? So normally to pass with a C, you need a 70%, and I'm gonna kind of just lower the floor down to a 60%. And that, again, that's intended for students who are kind of struggling the most, just so that these students will still get a passing grade in the class to kind of complete the stats major. And so, so I'm lowering the floor down to 60%, and I think that will help. And so small adjustments from there. So 70 C plus will go from 70 to basically 78%, B minus, yeah, 78 to 80.9, B 81 to 85.9, and B plus 86 to 89.9. Okay, and then I've adjusted the ranges for D and F as well. Okay, and I think after homeworks 4, 5, and 6, the grade scope and the is that it? Other stuff gets factored in it. I'll take a look at the distribution again, but I think this will reduce kind of the number of students in the not passing range. Okay, I'm also going to make just a very minor change to the homeworks. Okay, so in the original syllabus, I have 6 homework assignments where none are dropped, and each one is worth 4.5% for a total of 27 percentage points for the homework. And this year I'm gonna just adjust homework 6. Okay, so homeworks 1 through homework 5 are still going to be kept at 4.5% each. Okay, because I guess I was just reflecting back on, you know, when I was a student, it was always upsetting when there were like changes to the grading scheme, especially if it was like harmful to me, and even changes to the grading scheme that were helpful to other students. If it kind of reduced the weight of something that I scored well in or something, it was kind of, it bothered me. So basically, I think everyone's turned in homeworks, not everyone, but just most of you have turned in homeworks 1 through 4 already. Some of you have already made a lot of progress on homework 5. And so I don't want to make any changes to kind of the hard work that's already been completed for these homeworks. I don't want to kind of reduce that and say like, oh, all of this hard work that you've done already is suddenly going to be reduced in weight. So that's all being kept the same. But homework 6, which I haven't assigned, I'm going to reduce its weight to 2%, and I'm going to just give a free 2.5 percentage points to everybody. Okay, and so, you know, as the quarter rounds out, you know, if you find yourself overwhelmed with other classes and things like that, you know, you can make a calculated decision, and you can say, you know what, maybe I'll skip this homework. You know, you'll lose 2 percentage points, but in the grand scheme of things, it's not that huge of a deal, right? And if you get like, you know, a low score on homework 6, it'll only affect you a little bit. Okay, so homework 6, I'm reducing its weight, and then you can make a choice on whether you want to complete it. It's a challenging assignment, but I think it's a fun one, so I hope you do it. But again, what you decide to do, how you spend your last couple weeks of time, you know, that's up to you. So I'm going to reduce the weight of homework 6. Okay. As far as everything else goes, it's going to remain unchanged. So this everything else is going to remain the same. So 6 assignments, none are dropped, but now homework 6 has been reduced down to 2%. Okay, are there any questions? Are there, I guess, are there any objections to these changes that I'm making? So again, you know, these are, a lot of these changes are designed with kind of the struggling student in mind, just so, because I don't want to fail students, especially right now with, it doesn't seem right that on top of everything to fail a student that just might be struggling. So, so I'm just lowering the floor for what a C is. Okay. So yeah, I wanted to say this. You know what, and you know, with all of this talk about grades and all of this, I just want to say, you know, what you offer to the world is so much more than your academic achievements. Okay, so much more than your grades, your academic achievements, any of that stuff, right? I mean, I know what it's like to be a good student and to what it's like to get good grades, right? That was kind of my story in high school. I got good grades. I got into a good school and things like that. And everybody who comes to UCLA got good grades in high school, or at least their community college or whatever. You don't get into UCLA if you didn't have strong academics prior to coming here. I think part of the, a thing that comes along with that though is, at least for me, I had tied a lot of my identity to my academic achievements. You know, when I did well academically, I felt good about myself. When I did poorly academically, I didn't feel good about myself. And so, you know, it took me failures and actually, you know, maybe I'll tell you my story another day, but, you know, I had to actually drop out of the first university I attended for poor academic performance. And it was hard. And I think over time I've learned not to associate my academic achievements with my self-worth. And so anyway, I just want to affirm that that each one of you are people. Okay, you are a person capable of love, compassion, creativity. You know, the people that are closest to you, your family, your friends, you know, they care much more about your joy and your love for life than they do about your grades. Okay. You know, so anyway, I just wanted to say that, and I too, I care more about you as a person than about your grades. But you know, I understand that grades do play a role in things like grad school admissions, but I think, you know, while you are a student and in the middle of all of this, the emphasis that we put on grades probably is much more than we than they deserve. You know, grades and as far as grad school admissions go, grades aren't the only thing. You know, there's a lot of other factors that get factored in. And as far as people who are applying for industry, industry rarely cares about your GPA or your grades. Okay, and you're not required to put it on your resume. I mean, of course, if you've got a good one, you can. And truly, once you've been working for a couple of years, 2 or 3 years, and you want to apply for another job, they're not even going to check your GPA. They're gonna be more interested in what you've done at your last company. And so, you know, you might start off at just some random entry-level job and work hard and do well there, and that should help, you know, set you up for future success. Okay. It's always a little bit hard to say that your grades don't matter to students who, you know, through most of their life have cared about grades, and so I'm like trying to knock down these idols in your in your life, but anyway, I just want to say that. Okay, tomorrow is Thanksgiving Day, and it can be hard to be full of gratitude. When it feels like there's so much hardship in your own life, and also looking around, you see the world that we live in, and there's all of this kind of suffering, and but I still want to challenge you to take the time kind of this weekend to just reflect on the things and the people in your life that bring you joy, and I truly want you to do this. I want you to say aloud, maybe to yourself, just, I am thankful for whatever it is, right? I'm thankful for silly cat videos on the internet that make me laugh and stuff like that, right? Just whatever it is that brings joy to you. Say it out loud. And if it's a person that brings you joy, say it to that person, okay? Maybe you have to give them a call. Maybe you have to call them on Zoom. Apparently Zoom, well, I think Zoom is being free for Thanksgiving Day. But anyway, so I want you guys to say, I'm thankful for you, to the people that have brought you joy, okay? And I'll start, okay? And I'll start by saying, I'm thankful for you, my students who are here. And those of you who aren't here and you're watching on YouTube, the video, I'm still thankful for you also, okay? I can see the counts go up, and I'm glad that my videos are being watched, okay? Also, somebody is clicking like on my videos on YouTube, which is kind of silly, but funny, but also like, it feels good to see that number go up. So thank you to whoever you are that's doing that. So thank you. But more seriously, truly, I'm so thankful for you as my students. I consider it such a privilege to be teaching at UCLA, to be working with truly the brightest, the top 1% of students across the nation. And I see your eagerness to learn, and that brings me joy. I'm thankful to everybody I've had a conversation with during office hours, whether it's just about what's happening in your life, or just future plans that are going on. Future plans for attending school or finding a job. Truly, I thank you for each of those conversations. It means there's trust in this relationship. You value my opinion, and so thank you for all of you. Even the ones, even kind of my least favorite of the office hour visits, where I have to get in an argument about points and stuff on a assignment or something. Those conversations still show me that you care. You care about your schooling and your learning and your academics. And so thank you to each one of you as students. Thank you to those of you who are watching online. So anyway, I want you guys to have a happy Thanksgiving, and I wanted to just kind of throw that in there. Okay. So worst transition ever, but we're going to continue on in lecture content and material and talk about hierarchical models. So, let me give you a couple of quiz answers too. All right, so viewing quiz for today. I'll give you the first two. First two are A and B. I'll just give you all three, A, B, and C. Those are the view quiz answers for today, A, B, and C, okay? But stay on, don't just quit the call now that you have your three viewing quiz answers, or your or stop the video. But the view quiz answers are A, B, and C, and we'll introduce hierarchical models here. All right, so hierarchical models. This is a concept in Bayesian statistics, okay? And they work very well for the Gibbs sampler, okay? So let's just talk about the Gibbs sampler again, okay? So in the Gibbs sampler, we have a target PDF that we want to draw samples from, okay? This target PDF could be in high dimensions. So we have got d dimensions. And at time t, our current vector x at time t, consists of d values, each kind of with this, subscript t, okay? And what we want to do is we want to draw another value. It's a Markov chain after all, based on kind of our current values and things like that. So we're going to produce the next draw, which is going to be the values at time t plus 1. And instead of trying to propose the new coordinate in all d dimensions, what we're going to do is we're going to draw values from univariate conditional distributions. Okay, so we're going to we have to factor the joint distribution into a bunch of univariate conditional distributions, which can be a difficult thing to do. But if you do that, we're going to just draw x1 from the distribution of x1 conditioned on everything else. We're going to draw x2 from the distribution of x2 conditioned on everything else. We're going to draw x3 from the distribution of x3 conditioned on everything else, okay? And so when you do try to draw the value for x3, it's going to be the conditional distribution using the latest values of x1 and x2, which were drawn in previous steps. And then you will use kind of the most recent values for x4 through xd, which will be the most recent values are taken at time t. Okay, and so this is kind of the schema where x in the ith dimension for t plus 1 is drawn from the conditional distribution of x sub I, conditioned on all of the other values, which is the latest values at time t plus 1 for x1 through the previous value xi minus 1. And also the most recent values will be at time t for all the values that come after xi. So xi plus 1 through xd will be coming from time t. Okay, so that's the Gibbs sampler. All right, the Gibbs sampler works well for hierarchical models, okay? Hierarchical models are set up where each kind of parameter is conditioned on a different, what we call in this hierarchy of distributions, okay? So trying to figure out these conditional distributions won't be necessary. They're going to be kind of inherent to the hierarchical model setup, okay? So I want to revisit the Bayesian beta binomial baseball example, okay? So, we did this beta binomial baseball thing earlier where we said every player has some random variable theta, which is their batting average, okay? So a player has a batting average, which we're going to call theta. And we can think of the batting average as, the probability of getting a hit during an at-bat, okay? And when we did our beta binomial model, we said that the prior distribution for theta is a beta distribution. And we had shape parameters 81 and 219. And when we did that, if I go all the way back to week 1, I think we said, so this is kind of week 1. I hope you guys remember this. We said, if we pick the parameters 81 and 219, we would get a distribution that looks kind of like this, where pretty much all the values are above 0.2 and below 0.35, which is pretty much where baseball averages are, okay? So to qualify for Major League Baseball, you need to have a batting average over 20%. And, it's very, very challenging to get a batting average over 350, okay, 0.35. But at the same time, these choice of 81 and 219, these feel like arbitrary choices. And we ended up choosing these because it kind of produced this prior distribution. We said, hey, we kind of like this shape. We like kind of the properties of this prior distribution. And that's how we settled on the numbers 81 and 219. Okay. In a hierarchical model, okay, in a hierarchical model, we will not choose the parameters of the prior distribution arbitrarily, okay? So we're not going to choose 81 and 219 in this arbitrary fashion where we say, let's use that. What we will do is we treat the values of alpha and beta as random variables themselves, okay? So we're going to say this number alpha is the result of a random process. This number beta, 219, is the result of a random process. So it's going to be a random variable with its own random distribution or probability distribution. Same thing as beta, okay? And so alpha and beta, these are parameters of the prior distribution, and we're going to call these things hyperparameters, okay? So these are the parameters of the prior distribution. So they are hyperparameters, whereas theta is a parameter for the data, right? So the data come from a Bernoulli distribution, and theta is the parameter that determines the Bernoulli outcomes of hits or outs. Whereas the alpha and beta are parameters of the prior distribution, and they determine the shape of the prior distribution, and so they are called hyperparameters, right? All right, and so the distribution that determines alpha and beta is called a hyperprior, okay? The random distribution that produces alpha and beta are known as hyperprior distributions. Oops, I forgot to change these to the Greek letters. Hyperprior distributions because they produce the hyperparameters of alpha and beta, okay? So this is known as the hyperprior. So there's we're going to see the words hyper like a whole bunch of times. Is that okay? So we said, so alpha and beta determine the prior distribution, the beta prior distribution, okay? And currently alpha and beta are like 81 and 219, but we're going to say instead of setting the 81 and 219 arbitrarily, they're going to come from their own prior distribution called a hyperprior distribution. And the hyperprior produces the hyperparameters. Now, so if they're coming from their own distribution, this hyperprior distribution might have its own parameters, right? This hyperprior distribution has its own parameters. And so these are called hyperparameters, okay? I'm totally serious. That's what they're called. They're called hyperparameters. And oftentimes when you get to the hyperparameters, you can just choose them arbitrarily yourself. Or if you want, you can have another hyper distribution on top of that. So you would have this hyperprior with its own hyperparameters. And this can go on forever, okay? Now, at some point you stop. You can also use what's called an uninformative hyperprior, which is basically a flat distribution where all the values are kind of possible and stuff like that. But generally, but we'll get to this point where we're picking hyperparameters, and maybe we'll choose these a little bit arbitrarily, but it allows for a distribution where at least alpha and beta get are a little bit more part of the random process, okay? And this basically gives a little bit more, puts a little bit more emphasis on the weight of the data, okay? So rather than being strongly influenced by your choice of parameters for the prior distribution, which can be a bit arbitrary, we're gonna say, these will be, we'll kind of figure these out in a backwards fashion by drawing these, or setting up our hierarchical model, okay? So I'm modeling my thing based on chapter 9 of doing Bayesian data analysis. And so they choose, rather than having a separate distribution for alpha and a separate distribution for beta, these values will be determined by a constant omega, okay? So if we think about what alpha and beta, 81 and 219, represent, sometimes they're called pseudo counts, okay? So if you recall, the shape of the beta distribution is kind of determined by the number of yeses and the number of no's that you've seen, right? The number of successes and the number of failures. And we're basically aiming for some kind of, the mean ends up being alpha divided by alpha plus beta, and then the mode ends up being alpha minus 1 divided by alpha plus beta minus 1. And so, you know, prior to seeing any data from the player, we can kind of pretend that the typical baseball player who qualifies for playing in the major leagues might have 81 hits and 219 misses or outs. These aren't actual data values, but just imaginary counts of hits and outs that we kind of start off a new player with, okay? And then when we see the new baseball player perform, we basically add their observed counts to the kind of pseudo counts that we started off with. I hope that's okay. All right. And what we're going to do here is we're going to re-express alpha and beta as the result of a random process. Okay. So it means that there is a random distribution here, but the random process will be determined by this value omega. Okay. And omega itself is going to be kind of this proportion. So the mode of the beta distribution with alpha equal to 81 and beta equal to 219, the mode is right around 27%, just under that, 0.2685, okay? And this omega, we're going to say, is going to come from its own, this will be used to determine alpha and beta. So if you do omega times k being the sum of 81 and 219, okay, here we're going to say k is 300. If I do omega times k minus 2 plus 1, okay, we're going to get 81. And if I do 1 minus omega times k minus 2 plus 1, I'm going to get 219. Okay, that's going to be how we determine alpha and beta. So we're going to draw omega randomly. Omega is a random number between 0 and 1. It's basically a proportion, and it determines where the peak of our beta distribution is going to be. And we're going to determine alpha and beta using this formula. Omega times k minus 2 plus 1, and beta will be 1 minus omega times k minus 2 plus 1. Okay, and this is how we're going to determine alpha and beta. So omega is selected randomly. K we're going to just arbitrarily fix at 300. Okay, we could put a hyperprior distribution on k, but for now we're just going to look at the hyperprior distribution for omega. And so we're going to say omega comes from this random distribution, and this is a random number, and it's going to determine what alpha and beta are. So alpha and beta are going to be also random, but they're determined entirely by what omega is. Okay, so omega is going to be a random value drawn from a hyperprior distribution, and then the selection of omega will determine the values of alpha and beta. Okay, and so because omega is going to be a proportion, it makes sense that omega itself comes from another beta distribution, right? So this beta distribution that determines omega is the hyperprior distribution of omega, okay? And so for that, we're going to need to select some arbitrary values, these hyperparameters of alpha sub A sub omega and B sub omega. And so we'll just arbitrarily pick these to kind of produce values that we like of around, you know, 0.26, 0.27, something around there. So we're going to pick these values ourselves. So in general, the higher up you go, you're going to have more and more what we call uninformative hyperprior distributions. Okay. Okay, so this is kind of the hierarchy of random variables. Okay, so K is set to be 300. K is just an arbitrarily selected constant. A omega and B omega are also arbitrarily selected constants. We're going to draw a random value omega from this beta distribution. Okay. Okay, omega is a random value drawn from the hyperprior distribution. These parameters are arbitrarily selected. Okay, once we get omega, we're going to calculate what alpha and beta are. Okay, alpha is going to be omega times k minus 2 plus 1. Beta is 1 minus omega times k minus 2 plus 1. Okay, and these are just kind of back solving for what alpha and beta are, so that you end up with a beta distribution where the mode or the peak is located at wherever omega is located. Okay, and so these shape parameters alpha and beta are just determined by whatever random value omega is and the constant k, right? And they go into this beta distribution, which is our prior distribution on theta. Okay, and so the player's batting average theta is going to kind of be randomly drawn from this beta distribution. And then once we have the player's random, like if we're generating the data, once we have this, we put that into a Bernoulli distribution. This is kind of a proportion for the player's batting average. This will become our Bernoulli distribution, and that will determine the outcomes that we get of ones and zeros of whether the player got a hit or an out. So this is our hierarchy of values. I hope this is okay so far. Okay, and then I'm going to run out of time. That's all right. I spent a lot of time talking about, I don't know, things that I thought were more important. So anyway, okay, so here's the diagram. Okay, this is our hyperprior distribution. This is a beta distribution. And it's going to, from this hyperprior distribution, we're going to draw a random omega value. Okay, the random omega value determines what alpha is. So alpha is this, and beta is this. Okay, so this term is alpha, and this is beta. And so that determines a beta distribution with shape parameters alpha equal to omega k minus 2 plus 1, and shape parameter beta of 1 minus omega k minus 2 plus 1. Okay, that creates another beta distribution. From that beta distribution, we draw our batting average theta, and that batting average theta gets used in the Bernoulli distribution, which determines the outcomes of hits and misses. Okay, I think I'm going to run out of time. But basically, once we have this hierarchy, we can then start to model or explain the data of multiple players. But I think we're going to have to wait till Monday of next week after the Thanksgiving break to continue this lecture. So so we'll do that. We'll end here for today. Have a happy Thanksgiving, you guys. And yeah, I do encourage you to take some time to just reflect on things to be grateful for. I know it can be hard in the midst of stress and all of that, but I'm sure there are things that still bring you joy in your life. And so reflect on those, be thankful for them. And if it's a person that's bringing you joy, please do let that person know that you are thankful for them. So I'm thankful for you guys again. Have a good weekend and happy Thanksgiving. So we'll see you guys on Monday.